So, we will continue our discussion on principle of hydraulic machines and system design. Today, we will discuss about the degrees of reaction and efficiencies. Probably we have discussed about the degrees of reaction in the context of the discussion of pumps, but again we will recapitulate that and we will try to discuss that how velocity triangle is a function of degrees of reaction, and for different magnitude of rather different values of degrees of reaction, how can we construct the velocity triangles, and of course the component of velocities, I mean component of absolute velocity and component of relative velocity in the tangential direction changes with a change in degrees of reaction. We have defined what is degrees of reaction. So, again I am writing that what is degrees of reaction. So, this is very important in the context of pump and turbine operation, because as I said you that based on the magnitude of degrees of reaction, velocity triangles changes, and probably if velocity triangle changes, then of course the efficiency and of the total guide vane, blade, every design will change. So, we will discuss about the degrees of reaction today, but so we will define what is degrees of reaction. So, probably I have defined again, but today again I will recapitulate what is degrees of reaction. So, I am writing degree of reaction, we sometimes call it R, which is defined, probably I have written in the context of discussion of pumps, again I am writing that it is defined as the ratio of ideal static pressure rise, across the rotor to the total pressure rise across the stage of the machines. So, therefore, R, which is defined that total pressure rise across the stage to the ideal static pressure rise across the rotor to the total pressure rise across the stage. So, now before I go to discuss about the if I try to derive the mathematical expression of degree of reaction in the context of operation of pumps or turbine, let us first discuss about what is rotor and what is stage. So, we have discussed that rotor, that is a rotating part of a turbo machines, it is impeller for a pump and it is runner for a turbine. So, whenever fluid is approaching, rather fluid is passing through the rotor, rather rotating part, there is a static pressure rise and total pressure rise across the stage, because stage is not only the rotor, stage is the combination of stator plus rotor. So, I will now discuss about what is stage and what is how the how we can call it stage, two stage, three stage machine like this. So, if I talk about an axial flow machine, so if I take an example of an axial flow machine, suppose this is an axial flow machine. So, we have this is the impeller. So, let us this is axial flow pump or machine, whatever it is. So, this is rotor and we may have another blades which is hanging from the casing. So, this is casing and this is rotor which is rotating, but this is known as stator. So, stator, this is not rotating. So, rotor is a rotating equipment, rotating components of the machine. If we talk about axial flow machine, so the impeller is a rotor and we may have a stator, the blades which is hanging from the casing, but those are not rotating. So, stator, I will write that stator is not moving So, only since it is not moving, so relative velocities are absent. So, whenever we are talking about, in fact, I would like to discuss in this context here that when I am applying Bernoulli equation in the rotating frame of reference, always I write, always we should write that relative velocity, because their absolute velocities are replaced by the relative velocities. Since stator is not rotating, so stator is not moving, so only absolute components of velocities, absolute component of velocities are there, velocity is present, velocity is present. Stator is not moving, so only absolute component of velocity is present across the stator. So, if I draw I mean a rotor and stator combined, so it may be a one stage rotor, and this rotor plus stator, these two called a stage. So, this is one stage, single stage. So, I have one rotor and we have a stator which is hanging from the casing. So, this is a single stage machine. So, this rotor plus stator combined is called stage. Stator is not moving, only the absolute component of velocity is present over across the stator. Now, if I draw the combination of stator plus rotor, suppose this is if I write suppose this is rotor, and here we have three components. Let us say this is absolute velocity, this is tangential velocity, this is relative velocity. So, this is C1, this is W1 and this is U1, but the again from outlet from the rotor we are having three component of velocities. One is C2, this is W2 and this is U2, but when we have only stator, so stator so this is stator. So, maybe the C2 is approaching the stator and the velocity is coming out from the, so this is C2, so this is C3 which is axial. So, this is combinedly it is called stage, this is called stage. So, total pressure drives across the stage including rotor plus stator, while ideal stator rise pressure rise across the rotor. The ratio of these two quantities is known as degree of reaction. So, we have drawn a particular case and we have shown that what is stator, what is rotor, and as I said you that stator is not moving, so only absolute velocity component is present there. So, C3 which is coming out from the rotor from stator is in the axial direction. Okay. So, now it is very important to note that whenever fluid is approaching to the stator, we may have different angle. So, that will be very much important while we will try to have a mathematical expression of the degree of reaction. So, now if I draw say one rotor. So, if I draw one rotor, so this is rotor. So, if I draw the velocity component, so maybe this is the tangential velocity, this is absolute velocity, this is relative velocity and this is absolute velocity C1 and this is W1. So, this component is C theta 1, this is C theta 1 and this is W theta 1. Now, this angle is let us say alpha naught and this angle is alpha 1 and this is if I talk about axial flow machine, this is definitely CZ1, right. Similarly, whenever liquid is coming out from the rotor, so again we will have tangential velocity, we will have a absolute velocity and then relative velocity. So, this is W2, this is C2, this is U2, and we will have W theta 2, C theta 2, and this is CZ2. So, CZ1 and CZ2 are the flow velocities. So, for axial flow machine, it may be a pump or turbine. If it is axial flow pump or it is axial flow turbine like Kaplan turbine, axial flow machine, CZ1 equal to CZ2 equal to CZ and U1 is equal to U2 is equal to U. That is what we have discussed. Now, since U1 is equal to U2, so what I can write? C theta 1 plus W theta 1 is equal to C theta 2 plus W theta 2. Therefore, W theta 1 minus W theta 2 is equal to C theta 2 minus C theta 1. So, this is very important relationship for axial flow machine. Not only that, so if this is alpha 2 and this is alpha 3, this is alpha 3 and this is alpha 2. So, we need to know what is this, what are those angles. So, alpha naught I am writing alpha naught is equal to, alpha naught is identified by the absolute flow angle, at inlet, and alpha 1 is essentially relative flow angle at inlet. Similarly, alpha 2 is the relative flow angle at the outlet, and alpha 3 is absolute flow angle at outlet. So, these 4 angles are very important. So, absolute flow angle at the inlet, relative flow angle at the inlet, relative flow angle at the outlet, and absolute flow angle at the outlet. So, these are very important angles which we need, because while we will try to derive the mathematical expression for the degree of reaction. Fine. So, now with this, let us move to derive the mathematical expression for the degree of reaction. That is very important, because as I said you that today we will try to draw the velocity triangles for different magnitude of degrees of reaction, and not only that, we will see that how blade angle and these angles are changes with a change in magnitude of degrees of reaction. Okay. So, as I said you that R, that degree of reaction which is defined as the ideal static pressure rise across the rotor to the total pressure rise across the stage. We have now seen that what is called stage and what is rotor and what is stator. So, rotor plus stator, these two combined is called as a stage, and since stator is not moving, only the absolute component of velocity is there. So, this is the total degree of reaction. So, now R is, if I try to recall the definition, what is R? R is basically ideal static pressure rise, static pressure rise across the rotor. So, static pressure rise, I am writing again, across the rotor to the ideal total pressure rise, across the stage. So, what is, because all we are talking about ideal total pressure rise and static pressure rise. So, what is ideal static pressure rise across the stage? So, if I assume that P2 minus P1 delta P, that is the ideal static pressure rise across the rotor, divided by total pressure rise across the stage. So, that is total pressure rise across the stage, that, so total pressure rise across the stage. Now, see, as I said, the stage is equal to rotor plus stator. So, no pressure change is across the stator. So, stage is equal to rotor plus stator, and no pressure rise or pressure change, no pressure change, no pressure change across the stator. So, across the stator no pressure change. Therefore, what I can write, if I talk about, let us say pump, if I take an example of axial flow pump, then H is equal to, I know that U2 C theta 2 minus U1 C theta 1 by G. If we talk about axial flow pump, so if I talk about axial flow pump, then this H will be equal to U into C theta 2 minus C theta 1 divided by G. So, what is H? Essentially H is equal to delta P by rho G is equal to U into C theta 2 minus C theta 1 divided by G. Therefore, delta P is equal to U into C theta 2 minus C theta 1. So, delta P by rho G is equal to head developed. This is the head developed. So, for axial flow pump, the head developed is equal to delta P by rho G, where delta P is the total pressure rise across the stage, because if stage is rotor plus stator, there is no change in pressure across the stator. So, therefore, this delta P, if I go to the next slide, so this delta P is the change in pressure. This is change in pressure, rather pressure rise. Pressure rise is equal to U into C theta 2 minus C theta 1. Therefore, degree of reaction R is equal to P2 minus P1 divided by, that is, we have defined that U into C theta 2 minus C1 delta P divided by total. What is total? Total is rho Q into, rho into U into, if I go to the next slide, then delta P is equal to into rho. So, if I write, if I go to the next slide, then this is rho into U into C theta 2 minus C theta 1. So, this is the degree of reaction P2 minus P1 divided by rho into C theta 2 minus C theta 1, where P2 minus P1 is the static pressure rise across the rotor divided by total pressure rise across the stage. Since there is no pressure rise across the stator, so rho U into C theta 2 minus C theta 1 is the pressure change or pressure rise across the stage. So, now if I draw the velocity triangle, rather if I go back to the velocity triangles, that is what we have drawn in the previous. So, what I can write, as I said you, that if I apply Bernoulli equation, of course in a rotating frame of reference, then instead of absolute velocity, I need to write the relative component of velocity. So, if I write Bernoulli equation, then I can write P1 plus half rho W1 square is equal to P2 plus half rho W2 square. So, this is, if I write Bernoulli equation across the rotor, then what I can write? I can change, that is, if I write Bernoulli equation across the rotor, then I can obtain this expression and I can write P2 minus P1, that is a change in static pressure. This is the change in static pressure, across the rotor is equal to half into rho W1 square minus W2 square, right. So, I can write it half into rho. What is W1 square minus W2 square? That is equal to, I can write W theta 1 square minus W theta 2 square, because see W1, that I can obtain from the velocity triangle. What is W1 square? Because if I go back to the velocity triangles, then I can write W1 square is equal to Cz1 square plus W theta 2 square. So, here that is W1 square equal to Cz square plus W theta 1 square, and W2 square equal to Cz square plus W theta 2 square from velocity triangle. From velocity triangles, at the velocity triangles at inlet and outlet, right. So, velocity angles at the inlet and outlet we obtain this, and we can write that the change in static pressure rise across the rotor is equal to this. So, I can write that W1 square minus W2 square is essentially W theta 1 square minus W2 square. Therefore, W1 square minus W2 square will be equal to W theta 1 square minus W theta 2 square. So, that will be equal to half rho into W theta 1 plus W theta 2 into W theta 1 minus W theta 2. That therefore, this degree of reaction P2 minus P1, that is equal to half rho into W theta 1 plus W theta 2 into W theta 1 minus W theta 2 divided by rho u into W c theta 2 minus c theta 2 minus c theta 1. Therefore, that is equal to how much? Because c theta 2 minus c theta 1, c theta 2 equal to u minus W theta 2 and c theta 1 is equal to u minus W theta 1. Therefore, c theta 2 minus c theta 1 will be equal to W theta 1 minus W theta 2. So, that will be equal to, I can write W theta 1 plus W theta 2 into W theta 1 minus W theta 2 divided by u into W theta 1 minus W theta 1 minus W theta 2. Therefore, by 2, the degrees of reaction is W theta 1 plus W theta 2 divided by twice u. So, this is the final expression of mathematical form of the degree of reaction, that is what we obtain. So, if I go to the next slide and I can write that the degree of reaction, that is what I obtain, degree of reaction that is I obtain is W theta 1 plus W theta 2 divided by twice u. So, this is the mathematical expression for the degree of reaction for axial flow machines. I have to consider axial flow pump. Now, if we talk about turbine, of course, the direction will change. So, c theta 1 minus c theta 2, accordingly everything will be changed. So, that is only the change in the sign, otherwise degree of reaction is remaining, the mathematical expression for the degree of reaction is remaining same. Now, we have to proceed to see how we can mathematically give a how we can drive that the that is what I said, that the degree of reaction is a function of velocity angle, and how we can get the velocity angles for different magnitude of degree of reaction. So, I am writing, therefore, since it depends upon the velocity components W theta 1, W theta 2 and all those things. So, degree of reaction is a function of velocity angles. So, this is very important. So, now if I try to express, suppose we have a rotor, suppose we have a blade, we have blades, and if we draw the velocity angles, say this is u1, this is c1 and this is w1. So, this is let us say alpha naught, this is alpha 1, that is what we have discussed, and this component is c theta 1 and this component is w theta 1. And what is the velocity angles at the outlet? So, this is Cz1 and velocity angles at the outlet is, this is W2, this is C2, this is U2, this is W theta 2, this is C theta 2 and this is Cz2. So, this is alpha 2 and this is alpha 3. So, that is what alpha naught, alpha 1, alpha 2, alpha 3, that we have already identified what are those, we have given their name. So, relative and absolute flow angles in the at the outlet and inlet respectively. Okay. Now, if I talk about axial flow machine, so U1 is equal to U2 and CZ1 is equal to CZ2 is equal to CZ. So, for the axial flow machine. So, we are talking about axial flow machines, axial flow machine. So, this is the case. Now, degree of reaction R is equal to, we have seen that W1 plus W theta 2, W theta 1 plus W theta 2 by twice U, right. So, I can write it that 1 by twice U into CZ1 and W theta 1, what is W theta 1? CZ1 tan alpha 1 plus tan alpha 2 CZ2. So, W theta 2 is equal to CZ1, since CZ1 is equal to CZ2 is equal to CZ, I can write it is CZ. So, CZ tan alpha 1 plus tan alpha 2, therefore, I can write CZ divided by U into half of tan alpha 1 plus tan alpha 2, that is, now this phi is known as flow coefficient, this is called flow coefficient, this is called flow coefficient, that equal to Cz by U. For pump, see this is for pump, it is Q by ND cube, that is what we have derived from Buckingham pi theorem. So, Cz by U is equal to flow coefficient for compressor or turbine. So, for compressor or turbine, this is for compressor or turbine, this is Cz by U, and this is what we have derived from Buckingham pi theorem, that is Q by ND cube, right. Now, so this is phi by 2, this is phi into half into tan alpha 1 plus tan alpha 2, that is what the degree of reaction. As I said you that the degree of reaction is a function of velocity angle. So, is a function of velocity angle. So, that is why we have obtained phi. Now, what is phi? So, this is let us say equation 1. So, what is phi? Phi is equal to Cz by U. So, how I can write Cz by U? Because I can write U is equal to what? W theta 1 plus C theta 1 divided by U, divided by Cz, sorry, divided by Cz, because U is equal to W theta 1 plus C theta 1 at the inlet divided by Cz, therefore 1 by W theta 1 by Cz plus C theta 1 by Cz. So, phi is equal to, I can write 1 by W theta 1 by Cz, Cz or Cz1 same thing. So, what I can write, this is essentially tan alpha 1 plus C theta 1 by Cz, essentially tan alpha naught. So, I am writing this equation 2. Again I can write phi, that is flow coefficient for compressor or turbine, that is equal to 1 by U is equal to, again I can write this is W theta 2 plus C theta 2 divided by Cz. So, again I can write 1 by W theta 2 by Cz is equal to how much? W theta 2 by Cz is equal to tan alpha 2 plus tan alpha 3. So, this is equation 3. So, we have derived that the flow coefficient can be expressed in terms of different angles, flow angles at the inlet and outlet, relative or absolute, whatever it is. So, and also we have defined the degree of reaction in the context of axial flow machines. So, R is equal to, we have seen that R is equal to phi by 2. If I go to the previous slide, then R is equal to phi by 2 tan alpha 1 plus tan alpha 2. So, R is equal to phi by 2 tan alpha 1 plus tan alpha 2, right. Now, we will discuss our different cases, So, let us consider the magnitude of, that is what I was discussing, that if the magnitude of R changes, let us say 0.5, 1, 0. So, if I take a special case, R is equal to 0.5, R is equal to 0.5, that means half is equal to phi by 2 into tan alpha 1 plus tan alpha 2. Therefore, this is what is obtained. Now, 1 by phi is equal to tan alpha 1 plus tan alpha 2. So, for r is equal to 0.5, 1 by phi is equal to tan alpha 1 plus tan alpha 2. Now, from equation 2 I can write 1 by phi will be equal to tan alpha naught plus tan alpha 1, and from equation 3 1 by phi will be equal to tan alpha 2 plus tan alpha 3, right. So, if this is equation 4 and this is equation 5, this is 6. So, comparing 4 and 5, comparing 4 and 5, what we obtain? Alpha 2 is equal to alpha naught, alpha 2 is equal to alpha naught. Similarly, if we comparing 4 and 6, what we obtained? We obtained alpha 1 is equal to alpha 3. So, that means for a magnitude of degree of reaction 0.5, we have obtained that alpha 2 is equal to alpha naught and alpha 1 is equal to alpha 3. So, what this indicates? So, it indicates that velocity triangles are mirror images. So, this indicates velocity triangles are mirror images. This is very important, that for degree of reaction, as I said you that degree of reaction is a function of velocity triangle. So, for a particular magnitude of degree of reaction, let us say 0.5, we have seen that the velocity triangles are mirror images. So, alpha 2 is equal to alpha naught and alpha 1 is equal to alpha 3. So, if you draw the velocity triangle for r is equal to 0.5. So, r is equal to 0.5. If I draw the velocity triangles, we have a rotor and we have a stator. So, if we have a rotor, so this is rotor, and then we have this is C1, this is W1, this angle is alpha naught, this angle is alpha 1. Similarly, this is let us say outlet velocity triangle. So, this is W2, C2, this is alpha 3, this is alpha 2, this is U2, this is U1, and we have a rotor. So, we have a rotor, so this is stator. So, stator plus rotor is a stage. So, the velocity triangles are mirror images if degree of reaction is equal to 0.5, that is what we have seen. Now, question is velocity triangles are mirror images for each other. So, velocity triangles are mirror images each other for degree of reaction 0.5. So, the conclusion is velocity triangles are mirror images each other. So, that is what we have seen for degree of reaction 0.5. Fine. We can have a combined velocity diagram, and probably normally what do? We dimensionalize every term. So, if we draw the combined velocity diagram, so let us say, as I said you, the angles are mirror images. So, if I draw that combined velocity diagram, so velocity triangles are mirror images. So, this is C1, this is C2, this is W1, this is W2, and this is let us say AB. So, this is C theta 1, this is C theta 2, and right. So, this is the combined velocity diagram, and if I make the equation dimensionless divided by u, that is what you will obtain. So, this will be the component, that will be w theta 2 plus w theta 1 minus w theta 2 divided by 2, that is equal to w theta 1 plus w theta 2 divided by 2. So, r is equal to half is equal to w theta 1 plus w theta 2 divided by twice u. That means r will be how much? W theta 1 plus w theta 2, that is by 2u. So, therefore, divided by, if I make the equation, so if I make the equation every term dimensionless, so if I divide by 2 by u, then it is twice u. So, this is for r is equal to 0.5. So, velocity triangles are mirror images, right. So, why? Because this is w1, so this is w theta 1 and this is w theta 2. So, this quantity will be w theta 1, so this is w theta 1, this will be w theta 1 minus w theta 2 divided by 2 plus w theta 2 is equal to this quantity, and this is degree of reaction r is equal to 0.5. So, this quantity is w theta 2 plus this one. So, this is p into p cube. So, p cube is equal to w theta 2, I have made it dimensionless by u, w theta 2 by u plus this small quantity, that is w theta 1 minus w theta 2 by twice u, and it is w theta 1 plus w theta 2 by twice u, that is equal to r is equal to half, that is w theta 1 plus w theta 2 is equal to 1. Now, I will take a special case, say we will now again take an example, special case, r is equal to 0. R is equal to 0, what will be the special case? Because we need to know what is r will be 0. So, for r is equal to 0, that is ideal static pressure rise will be equal to 0, that is P1 will be equal to P2. So, example is P1 will be equal to P2. From definition of the degree of reaction, we can say that r is equal to 0 means ideal static pressure rise will be equal to 0, that is P1 is equal to P2. That means example is Pelton wheel. Example is Pelton wheel. Why? That water strikes at the wheel at atmospheric pressure, also leaving the wheel at atmospheric pressure. So, why? Because water strikes the wheel at atmospheric pressure and leaves the rotor, wheel at atmospheric pressure. So, that is P1 is equal to P2. So, for Pelton wheel, an example of degree of reaction is equal to 0. So, we have to draw the velocity triangles for again degree of reaction is equal to 0. So, if r is equal to 0, then what will be the case? So, for r is equal to 0, P1 plus half rho W1 square is equal to P2 plus half rho W2 square. That since P1 is equal to P2, therefore W1 will be equal to W2. W1 will be equal to W2, right? Or else, if I recall the definition, W theta 1 plus W theta 2 divided by twice u is equal to 0. Therefore, W theta 1 will be equal to minus W theta 2. So, what will be the velocity triangles? W theta 1 is equal to W theta 2. So, if you try to draw the velocity triangles, that is very important, because as I said, the degree of reaction is a function of velocity triangles. So, now suppose if I am drawing So, this is C1 and I am making dimensionless by u. This is W1 by u and this is u by u. Now, I have to rewrite it. So, say this is W1 this is C1. So, C1 by u, this is u by u, this is W1 by u, this is W1 by u, this is u by u. Now, W theta 1 will be equal to W theta 2. So, W theta 2 so this is W theta 2 W2 and this will be C2. So, this will be C2 by u and this is W2 by u. So, what is W theta 2? This is W theta 2 and probably this will be W theta 1. So, W theta 1 is equal to minus W theta 2. So, this is the case when r is equal to 0, that is W theta 1 you have to construct the velocity triangle in such a way that W theta 1 should be minus W theta 2, that velocity triangles are mirror images to velocity triangles are not mirror images, rather W theta 1 is equal to minus W theta 2 for r is equal to 0. So, this is the by u by u. So, this is the combined velocity triangles. Now, we will take another example. So, we have taken example of r is equal to 0, that is a special case. We have seen, we have drawn the combined velocity triangles and we have identified that how W theta 1 plus W theta 2 by twice u is the r is equal to 0.5. Then we have tried to a special case r is equal to 0, example is Pelton wheel, there is no change in pressure across the rotor and we have taken, and for that we have drawn the velocity triangles. Now, we will try to draw the velocity triangles for r is equal to 1, that is very important. So, r 0, 0.5 and 1, there may be another different cases, but so now r is equal to 1. So, if r is equal to 1, then what is r? W theta 1 plus W theta 2 divided by twice u is equal to 1, that is we have obtained, right. So, what is W theta 1? U minus C theta 1 plus u minus C theta 2 divided by twice u is equal to 1. Therefore, we obtain that what? That we have obtained twice u minus C theta 1 plus C theta 2 divided by twice u is equal to 1. Therefore, C theta 1 minus C theta 1 plus C theta 2 divided by twice u is equal to 1. Therefore, C theta 1 plus C theta 2 is equal to 0. So, we will obtain C theta 1 is equal to minus C theta 2. So, this is the our conclusion that C theta 1 is equal to minus C theta 2. So, what will be the velocity triangles? So, if I try to draw the velocity triangles, combined velocity triangle, then C theta 2 will be equal to minus C theta 1. So, velocity triangle will be like this, combined velocity triangle if I draw, then this is let us say C1 and this will be W1. So, this is W1 by u, this is C1 by u and this is u by u, that is always 1. So, this is u by u always 1. Now, what will be our C2 and W2, because this is C theta 1. So, this is C theta 1. So, now C theta 1 should be equal to C theta 2. So, C theta 2 may be this equal to C2, this will be equal to W2 by u, C2 by u and this will be equal to C theta 2. So, C theta 2 and this is C theta 1, C theta 2 is equal to minus C theta 1 and this is W. So, note that for this particular case W 1 is increasing, is higher than W 2, that is W 1 increases. So, if I try to draw the velocity triangle, suppose we have a rotor, right. So, we have a blades, right, and so this is rotor, this is C1 while W1 is higher. W1, this is C1, this is U1. Similarly, our outlet velocity triangle will be W2, C2, U2, and we have a stator part. So, this is stator part. So, this is stator, this is rotor. Note that for degree of reaction R is equal to 1, W1 becomes higher. So, if W1 becomes higher, so W1 increases, this is very important. So, relative Mach number MR1 is equal to W1 by A1 will be greater than 1. So, relative Mach number, that is relative velocity at the inlet increases for a degree of reaction 1. We have drawn the, this is a combined velocity triangle, this is combined velocity triangle. So, W1 becomes higher, relative Mach number, this is relative Mach number, will be higher. So, when R is equal to 1, when R is equal to 1, relative Mach number increases, and if relative Mach number increases, it will leads to several problems. I mean, it will leads to shock losses. Shock loss occur in case of compressor, in case of a compressor, and we have seen that if W1 increases, probably you have discussed this issue in the context of inlet swell in a pump. If relative velocity at the inlet increases, pressure will fall, and if pressure falls below the vapor pressure, local boiling may take place and it will lead to an undesirable phenomenon of cavitation. So, we have seen that for degree of reaction 1, velocity triangle will change in such a way that the relative velocity at the inlet will be higher, and it will leads to a higher value of relative Mach number, that it will create a shock losses in case of a compressor, or it will leads to a cavitation in case of a pump, or cavitation in case of a pump. So, this is very important. So, we have taken 3 different cases of R is equal to 0.5, R is equal to 0, R is equal to 0. Example is a Pelton wheel, there is no change in pressure across the wheel, I mean static pressure no change, P1 is equal to P2, P2 minus P1 is equal to 0, because water strikes the bucket at atmospheric pressure and leaves atmospheric pressure. We have taken example of R is equal to 1 for which, and we have taken axial flow machines, rotor and stator. Then what we see that from the R is equal to 1, R is equal to 1 itself will allow us to construct a velocity angle in such a way that W1 has to be higher. If W1 increases, then relative Mach number will be higher, it will create, it will leads to several undesirable phenomenon in different machines. In case of a compressor, shock loss, there will be a shock loss, and in case of a pump there will be cavitation. So, we have discussed about the degree of reactions and how the velocity triangle changes with a change in magnitude of degree of reaction. We have constructed velocity triangles in a combined plane. Also, we have constructed velocity triangles at the inlet of the rotor, outlet of the rotor, and in a stator there is no, as I said, there only absolute component of velocities are present. So, there are no, this since it is not moving. Okay. So, with this now we will discuss about efficiencies of turbine, that is, although we have discussed about the efficiency of a turbine because we have worked out example, but today I will discuss about efficiencies. So, turbine efficiencies. So, we have discussed that there are one is in a Pelton wheel we have discussed about the wheel efficiency or hydraulic efficiency is very important, that how we can discuss about the hydraulic efficiency or wheel efficiency. So one is wheel efficiency, that is we have discussed in the context of Pelton wheel. What is that? We have discussed that maybe what is power transmitted by the fluid to the wheel. So maybe power input to the wheel is not equal to, so as I discussed that power input to the wheel may not be equal to the power transmitted by the fluid to the wheel, rather whatever amount of power input to the wheel that is obtained from kinetic energy of the jet, power input to the wheel that is obtained from kinetic energy of the jet leaving the nozzle, either kinetic energy of the jet arriving at the wheel or leaving the nozzle, arriving at the wheel or leaving the nozzle. So the kinetic energy leaving the nozzle, that is a power input to the wheel, but whatever amount of power input to the wheel, it is not transmitted by the fluid to the wheel. So there will be a change, I mean difference because of losses. So this is known as wheel efficiency, and that is what we know, wheel efficiency eta W. And we have also discussed about that what is overall efficiency. Overall efficiency is very important, rather that what is overall efficiency, eta O. So what is power output from the turbine? So this is power output from the turbine. This is very important. Now what is the power input to the turbine? Suppose if I have Q meter cube per second flow rate, G and head available GH. So rho Q GH is the power input, rather power that is available at the shaft, while so this is the power available, and this is the power output from the turbine. So these two are not same because frictional losses, windage losses, bearing friction losses, all those things. So this is known as overall efficiency. And similarly you can define another efficiency known as hydraulic efficiency, just like a pump. Hydraulic efficiency in most of the cases, that is very important, that how I can define hydraulic efficiency, because U2 C theta 2 minus U1 C theta 1 by J. So U2 C theta 2, here for a turbine it will be C theta 1 minus C theta 2, because 2 is the outlet, by G into H. So now in most of the turbine the flow at the outlet from the runner is swirl free. So if flow at the outlet from the runner is swirl free, then it is U1 C theta 1 minus U2 C theta 2 by G. So in most of the cases the flow at the outlet of the runner is swirl free. So U1 C theta 1 by GH is the hydraulic efficiency, since flow at the outlet from the turbine, is swirl free, that is C theta 2 is equal to 0. Since C theta 2 is equal to 0, the hydraulic efficiency is defined just like a pump, but here the component of swirl velocity, the sign will be changed, because inlet is C theta 1, outlet is C theta 2. So U1 C theta 1 minus U2 C theta 2 by G, where C theta 2 is equal to 0 since outlet flow is swirl free. So U1 C theta 1 by GH, that is the H is equal to head available. So how much head is converted to the by the fluid. So U1 C theta 1 by G, that is the energy, how much energy you are getting. So this is known as the hydraulic efficiency. So these three efficiencies probably we have discussed while we are solving the problem, but now we have defined that these three are the efficiencies in the context of turbine operations. So today what we have discussed about the degree of reaction, we have defined degree of reaction, and then we have discussed about that the stage, what is called stage. We have taken an example of axial flow machines or axial flow pump, and then we have tried to derive the mathematical expression for the degree of reaction. From there we have taken three different cases, that three different magnitude of degree of reaction, and for that how velocity angles are changing. So with a change in magnitude of degree of reaction, velocity triangles are changing, and since we have taken example of r is equal to 0, 1 and 0.5, we have seen the r is equal to 0 is a case where there is no change in, I mean no rise in static pressure across the rotor, and example is Pelton wheel. And for all three cases we have defined, we have drawn the combined velocity diagram, and we have seen that for r is equal to 1, the velocity triangles takes a step in such a way that the relative velocity at the inlet becomes higher, and if relative velocity at the inlet becomes higher, relative Mach number will be higher, and it will leads to two different undrivable phenomenon for two different machines. If it is a compressor, then shock losses will be there, and if it is a pump, then cavitation might occur. And then we have discussed about efficiencies for the turbine, three different efficiencies, and probably we have discussed rather we have taken the formula of efficiency while we have solved the problem, but today we have discussed about their definition. So with this I stop here today, and I will continue our discussion in the next class. Thank you.